Okay, so whenever all of that happened, I lost everything that I had on the slide, so I tried to write it all back. I know that I missed a couple of things, but I think we're pretty much on the same page. Um, One thing I did want to point out though is why we're using 80 or alpha instead of 10 degrees is because the dot product is like these two vectors right here. So when you have this angle in between, that's when you use the dot product, okay? And I went ahead and I put this 10 degrees over here. I think I did that on the last one. But whatever this angle is this angle right here. And it just kind of shows you that 80 degrees is right in between those two vectors. And so we're doing the dot product of them. All right, so hopefully that makes sense. Now, we still have to find the speed at the bottom. So we had talked about that the change of kinetic energy is equal to work. We just found work with this 5,960. So you would do like final minus initial kinetic energy is equal to work. And then you would solve for the final velocity. So 1/2 mv squared minus 1/2 mv squared is equal to 5,960 joules. So if I go ahead and I move this over, so just add that over to the other side, okay? So I'm going to move over a little bit just so that I have plenty of room. So I have 1/2 mv squared is equal to 5,960 joules plus 1/2 mv initial squared. And I'm solving for that. So multiply by 2, but you have to multiply by 2 to all of it. So it ends up being 2 times 5,960 plus this 2 multiplied by half cancels that out. Okay, so that's gone. And then you've got divided by mass. Okay, so divided by the mass. Now, let me kind of erase that a little bit like that. So you got to divide it by both. Okay, well, what happens is you cancel that out right there. So you end up with 2 times 5,960 joules divided by the mass plus initial velocity squared. And this is still squared, so you have to do the square root of all of that. Okay, so if you do 2 times 5,960 joules plus the initial velocity was 2 meters per second squared divided by, sorry, I do not know why I did that because that is not there. This is divided by the mass of 70 kilograms, and all of that is under the square root. Okay, so whenever you do all of the math of that, let's see what we get for our answer here. 13 meters per second. Okay, so whenever you're given an initial velocity like that, whenever you do all of the math, you'll see that, that half and that mass cancels out, but just for it. Okay, so just kind of make sure your algebra is good with all of that. Okay. All right, so let's go on to the next. Let's see, this is saying that the figure is showing a particle that's moving in a circular motion at every point in the motion. The force, the static force, the component of the force is parallel to the instantaneous displacement. So this isn't the static force, sorry. This is the force with respect to the distance, the S. Okay, so the component of the parallel to the instantaneous displacement is 0. And you can see that, it's making this sort of perpendicular situation here. So again, because of that means that there is no work, because that would be like the cosine of 90. So on this one, this is saying that a car on a level road turns a quarter circle counterclockwise. And this is saying something that you learned in chapter 8, which we didn't do chapter 8. So this is talking about the static friction causes the centripetal acceleration. So the work done by static friction, but just really don't need to even go to that chapter, because if it's making this 90 degrees here, then you've got this force, and it's at this displacement that's tangent. So it ends up being the zero work. Okay. And then this is showing Newton's third law. So that's for every action, there's an equal and opposite reaction. So if the skater is pushing on the wall, then the wall is pushing on the skater. And it's saying that the skater's center of mass is displaced, but her palms is where the force is actually exerted. So her palms are not displaced. So because of that, at that point it says the force is acts, but the force doesn't push any physical thing through a displacement, so no work is done. Okay? So whenever the point of contact is displaced. Okay? So this is just saying that to calculate the work done on an object by force, that you should remember that if you were to be given, say, like a force versus position graph, since the work is basically the integral of the force times the change of distance, then that's the area under the force versus position graph. So there's an example. It says, but apparently there is not a graph. Is that right? I think I'm having like technical difficulties for some reason. All right, I'll just draw this. Of course, I'm having technical difficulties. I'm so bad at this stuff, guys. Like, thankfully, our Elmo never went out in class. Then, I'd have to write on the board, which is just awful. Just kidding. I mean, not really, because I used to do that all the time, and now that I've done the Elmo, I'm sort of spoiled because it's just it's my comfort zone. This is definitely not. I guess it's starting to become a little bit more comfortable, though. All right, so then it goes like this. Okay, so this is saying that a 1,500 kilogram car is towed starting from rest. Shows the tensional force. Going from 0 meters to 200 meters, what's the car speed after being pulled 200 meters? Okay, so work is the area under the curve. So 1/2 the force times the distance. Okay, so 1/2 times this 5,000 newtons times 200 meters. It's going to give you 500,000 joules. But then it says, what's the car's speed after being pulled 200 meters? And it does say that it starts from rest. So if we consider that, then basically we're going to do what we did on the last one. Our work is equal to our change of kinetic energy. So we've got final minus initial is equal to work. So we are looking for that. If our initial velocity was 0, then that goes away, because anything times 0 is 0. So, okay, we are looking for our final velocity. So we end up doing 2 times the work divided by mass, and you end up doing the square root. So 2 times 500,000 joules. Oh no. Divided by our mass, which was 1,500 kilograms, do the square root of all of that, and you should get 26 meters per second. Okay? So that's just a situation where if you do have an initial velocity, you can still set it up with a change of kinetic energy and then just cancel out one of them. Okay, I think I gave you 2 slides for that. Don't need them. All right, let's see. I think we're starting to get into restoring forces and things that are like if you have stretched or basically elastic potential energy. So I'm going to stop the video where I was and then start a new one and